Wrong button. Okay, here we go. Switch to slideshow. Can you see a slideshow if I talk?
Yep, sure can.
Okay, so this is an update on the status of the project named MagnetoViz. I presented it in January after a couple of months development, and so we've made a lot of progress since then. Briefly, MagnetoViz is a set of ParaView and Python tools for doing magnetosphere-related visualization. There's no reason we can't extend it to other domains, but we primarily focus on the magnetosphere. And so this is in collaboration with Dan Willing at UTA, Angel Guitar-Leon, who's done quite a bit of a development. He was a student at GMU, he's now at NRL. And then Gary Quizmia, who is a undergraduate at GMU, who's now at UVA. I thought it would be useful just to give you a whirlwind tour of what you can do at this point, just so you have an idea of what I'm talking about in the slides after that. I'm going to launch a script named MagnetoViz Demo, which is sort of the kitchen sink of everything that's possible, almost everything. And I shall pull that up here. Let me find the window. Okay, here it is. So to use MagnetoViz, you're going to have to learn a little bit of ParaView, at least in terms of the GUI and the user interaction. To develop MagnetoViz related things, we have a sequence of demos that show you how you can do things. And I'll talk more towards the end about development and how we're going to proceed with that. So this has launched a scene with quite a few of the possible objects that you can create. These objects in this scene was generated by selecting the objects as sources, and so they're listed under, oops, I forgot they're listed under the sources menu here, and then you can turn them off and turn them on and highlight various different things, and again to create a different scene. Of course, things are going wrong here. So we have a second angle plasma sheet. In the background here, we have, I believe it's a geotail satellite floating around, and it's color coded by the different magnetospheric region that it's in, according to SSC Web. So all of the data for the satellite trajectories are coming from SSC Web, which includes region ID. And so we color coded it by that. And then we have Earth, oops, zoomed in too much. We have a plasma sheet in here. I need to turn off a few things here. So we have a plasma phos based on one of the community models. And then we also have a feature where you can do, if you have data that's like a 2D image that you want to map to a sphere. So for example, 2D ionosphere currents, you can overlay that on top of Earth. So I know those are common visualizations people make, and it's pretty easy with this to overlay it so that you can look at that 2D plot wrapped around on Earth. And so that's the sort of essentially all of the different objects that you can create. And then I'll just show you a typical user interaction of what you do and how this all works. And I'll just delete these guys. So there are ParaView modules called macros. And here I have a satellite macro that automatically puts in a satellite over a certain time range and generates the plot for me. And I could have also done that by selecting it as a MagnetoViz, a satellite object, and it would create this trace And then on top of that, I would have had to create, apply a bunch of display options. And this macro has created the trace and also applied a lot of the different colorings and, the tube to the line and so on, and created this legend entry. And then another thing you can do is add a magnetic field model. So here I'll add a dipole. Now we have the dipole data loaded in on a grid, and I'm going to change this from -10 to 10, -10 to 10, -10 to 10, and I'm going to make 30 points in the X, 30 points in the Y, 30 grid points in the Z, and then apply. And so now it's loaded all of this data into a box that's 30 by 30 by 30 grid points. And that's not very useful to visualize. You can look at it as oops. Well, I'm just going to add some field lines since that's not, I forgot how that works. Oh, I'm not coloring. I need to color it by the magnetic field magnitude. And then I need to turn on the log scale, which I haven't done. So I am going to hide that and then do something that's a little more useful. Click up here. I can draw some field lines. This is going to draw a whole bunch of them. And so it's generated some field lines, and there are some artifacts there because of the grid boundaries. And then on the very interior here is a particle trajectory. So if you have a particle trajectory in a NumPy array, you can just dump it out and visualize it. And so that's the general idea of what we can do. How am I doing on time, Julie?
Hello?
You're doing great.
Oh,
You've got plenty of time. Technically, I gave about 15, 18 minutes for these to give plenty of time for questions. So if you want to go that long, you can end short, whatever.
Okay, when do I end?
I believe it's at 9:24. So you have 10 minutes, plenty of time.
Okay. So I'm going to try and leave a lot of time for questions then. So these are our primary objectives, and we've met all of these, and actually we're at the point where I've decided that we need to resist the temptation to keep on adding things and tidy up and make sure everything works and all of the settings are sensible. So there's a little bit of cleanup that needs to be done. And we've tried to make it as useful for domain scientists as possible. As I'll briefly touch on, if you have a function that creates some data, we have created a bunch of scripts such that you can just pass that array to one of our library functions, and then it'll be available in for rendering in ParaView. As an example, that dipole was actually created. All I needed to do, in principle, was to write this Python function, and then everything else, all of the visualization and everything on top of that was using this function. And so this is all I had to do. So if you want to define your own dipole or any kind of function that takes in some points and outputs a vector field, you can do that. And so here we have the T89C. We're using the Python GeoPack library to implement that, and TO1 as well, IGRF, and so on. So we tried to make it as simple as possible so that, just using NumPy and creating NumPy functions, you can get up and go and start visualizing. So the capabilities, you saw quite a few of them. The different magnetospheric objects, so a Sigonenko current sheet, a neutral sheet, a magnetopause, a bow shock, plasma pause you saw. You can also load in data from a CDF file. So the CDF file contains points and a vector field, and you can visualize it in the same way I did as the dipole. A somewhat big project was writing a code that would read the native BATS-RS grid files into Python. And so we spun that off into an external library because it's sort of, it's not necessarily about visualization. And I think it might be generally useful to others because it really starts out by loading in the data into Python. And then a minor piece of that project is to output it as a VTK file for easy reading. I've already mentioned that, you can just pass these things NumPy arrays, and ideally you don't have to do that much more in terms of learning about the internals of VTK and ParaView. We have these different magnetic field models, and you can plot particle trajectories. The particle trajectories I have are from an external library, a student project who is doing those particle integrations in Python. And so that's not distributed with MagnetoViz. Then we use the SSE web satellite trajectories obtained through the HAPPY API. And I already mentioned you can overlay 2D images onto an Earth sphere. And so the image I showed you was a satellite created image of Earth, and you can just do any PNG image that you want. The status is that all of the code for the capabilities I mentioned is written. This is the repository. There were two new projects that we kind of spun off. One is HX form, and it's a bunch of space physics coordinate transforms. Essentially, it sits on top of the SpacePy, and there's another library called CX form in C. And then there's actually a third library. And you can pick which one you want to use. Actually, the third library is that it has a hook directly into the Sigonenko GeoPack library. And you can pick which one you want to use. And the main thing with this is that we've tested and intercompared all of these different coordinate transformations. And the reason we just didn't go ahead and use one was in part because, as you can see, you need to do quite a few coordinate transformations, and speed is an issue. And so we had to address that, and some of those things were put into this package. And then Gary has created this space weather modeling framework file reader, which reads that data on the native grid, the adaptive grid, into Python. So the few things we need to finish that we're pretty close on is connecting all of the code to the ParaView menu. So I showed you that menu where you can connect, select different sources. One of the challenges there is setting up the appropriate menu options. So if I do source, MagnetoViz, if I do Sigonenko, so here we have to set in all the inputs for Sigonenko. In this case, it's the KP range and the dipole tilt, or just a time from which the dipole tilt is calculated. And so, setting up these menus takes a little bit of time, and there's still some limitations like not being able to order these things that we need to take care of. And that's sort of a tedious thing that requires a lot of research, but is possible. We need to finish up the documentation, of course, and simplifying the installation. Installation is a two-step process. Is one, you install ParaView, and two, you do a pip install of MagnetoViz. Actually, it's a three-step process because ParaView ships with its own version of Python, and so you have to set up a virtual environment with the same version of Python, or you might get surprises. It's not mandatory, but it's recommended. And then we have a bunch of tests, but we need to automate that. And then we have weekly developer meetings on Fridays at 4 p.m. Eastern, and I'll probably transition those into user meetings. So if you're interested in this project and you want to learn how to use things, you can start attending this meeting. And if you're a developer as well, you're welcome to join at Fridays at 4 p.m. Eastern. Okay, I wanted to leave time for questions.
Bob, any questions?
Yes, I have a couple. What about visualizing vector fields either along a spacecraft trajectory or out of a 3D simulation?
Yes, I wanted to add an example of that. It's possible. Yeah, and ideally, what we could do is with those spacecraft trajectories, with each trajectory, we would attach the vector fields that are available from SPDF data. But yeah, it is possible to add vectors to those lines, watch the vectors rotate around. I just don't have a demonstration of that.
And the other thing was isosurfaces?
Yeah, that's pretty easy to do. Well, maybe for Angel, to select one of these things and do an ISO surface. I forget which button it is, but yeah, that's easy to do with native ParaView tools.
Awesome. I see Baptiste, Rebecca, you have your hands up.
Yes.
Yeah, sure.
Okay, go ahead.
I'm sorry. Didn't know who was first. Yeah. Hey, Bob. So this is Rebecca with CCMC. We're working on updating from, if I understand correctly, working on updating from Chameleon to Komodo. So in the next several months, it would be interesting to work together to see how that works out.
Good.
Awesome. Baptiste?
Yes, thank you, Bob, for the presentation. That's a nice demo of what we can do with ParaView when we try to play along. I was just wanted to remind that there was just the question of Aaron who brought this comment. So there is a tool developed in Toulouse by the Plasma Physics Data Center, the French Plasma Physics Data Center, called 3D View. And 3D View can import models and display the same kind of thing that you've been showing to us. So I don't say that that this is a problem. It's good to have several tools that are doing things in a different way. But I think it would be worth maybe getting back to that tool to see what are the capabilities, to see how those things were solved in that context. And Aaron saying that he wanted to plot vector quantities, data along the spacecraft trajectories, and this is exactly something that 3D View is doing very well. And then just the last comment is that at the time, maybe 5 years ago, there was the IMPEX project that was funded in Europe, who led to the space extension for simulation runs. And within that frame, there was some web services interfaces that has been developed so that tools can query databases containing simulation runs, 3D simulation runs, and extract slices or time series along a space trajectory that along a trajectory that would be fed to the interface. So that's something that was very helpful and still used actually by 3D View with a few data centers in Europe. So it would be probably very good to try to interface also to that.
And what is it? It's called 3D View. Is there another keyword that you can search on?
3D View, yes. If you search 3D View and CDPP, you will find it. The URL is yes, it's there. It's in the chat. And so it's a Java tool, so it's a different perspective. So it's not as configurable as Python, but it has a lot of capabilities also.
Yeah, that was one of the reasons we went with ParaView, I guess, is because we wouldn't have to maintain sort of the internals, just the external scripts. There were a couple of Java programs, actually. I think we looked into this as well, but I think certainly there's a lot of pieces.
So this is why I say that it's good that there are several tools with various capabilities. Having ParaView, an interface and ParaView is much more flexible for sure. But depends what the users wants to do.
Sure. Yeah. Yeah, and it's also useful. We found it very useful. I think we were using tipsod when we were doing these satellite trajectories, trying to figure out if we were doing them right or plotting the plasma pause, because it's difficult to implement those models based on when you're reading the papers.
Yes.
There's always some ambiguity.
Yeah. The good thing I would say with 3D view is that everything is already set up with the spacecraft trajectories, the bodies, the location of the body. It's using SPICE behind to compute everything. And then it connects both to simulation runs and in situ data. So with the AMDA database, so you can plot whatever spacecraft with in situ data, you can plot the data on the trajectories and also overlay model runs. So this is something that probably you want to do too. So yeah.
Great discussion, all. Feel free to continue this in DMs and offline. We need to move on to our next presentation, though. Thank you, Bob. So the next up is Grant Stevens. He'll be presenting on MPI, EMMPI. Let us know how we should say that.
MPI.
Awesome, thanks.
I cannot share.
Oh, interesting.
I know.
Okay.
Oh.
Let's see.
Yeah, now it's working.
Oh, okay, cool.
Slideshow. Okay, does this look right?
So far we're seeing kind of the editing mode.
Here, is that better?
Still the editing mode. Is it going up on two different monitors?
Yeah, let me turn this one off.
Never seen it do that before.
So-
Yeah,
Does it look good now or not?
it's a little cut off.
It looks fine from my vantage point. Does this still look bad?
We just see a long vertical bar, a bunch of fun geometric drawings.
You probably need to unshare and then reshare your screen again.
Yeah.
Okay. Okay, how's that?
That's great.
Okay.
Yep.
So I'm presenting on the on MPI. So MPI stands for Empirical Magnetic Field Modelings in Python. So this was a HDEE grant that we had funded to basically translate our latest empirical magnetic field model from kind of this Fortran style code that I then translated to Java a few years ago. And we wanted to make it also available in Python natively. So a brief introduction to these empirical magnetic field models and what they're used for. So that what they try to do is empirically and analytically describe the primary current systems that exist within the magnetosphere, and then fit those current systems in analytical expressions to the available magnetometer data from spacecraft. So these kind of differ in comparison to first principle models, which actually try to describe the underlying physics from either Maxwell or Vlasov equations and describe the system that way. Empirical models just try to use these general analytical descriptions and then fit those to data. And the advantage of empirical models is they tend to evaluate much quicker than having to use first principle models where you have to go run an event and wait for it to run and come back. And because of this, they're quite widely used, particularly because of this frozen in flux effect, that the knowledge of the magnetic field really lets you correlate observations by using magnetic field line tracing. And it also, the magnetic field can be related to other plasma quantities like the current density and also the plasma pressure. So, and another thing, these type of models are often used to compute the 3 adiabatic invariants because you need to know a global knowledge of the magnetic field to compute these. So they're often used in different types of particle applications that need to know these invariants. So our motivation behind this was that most of these models, even though they're widely used in the heliophysics community, they were mostly written in Fortran and using kind of the common coding practices that was used in the 1970s. They're kind of frozen to that era of software design and practices. So for example, the TS07 model, so this is the model I've primarily worked with, is it's one source file and it's about 5,000 lines long, and it doesn't use any of the modularity or revision control like a modern software architecture would use. The other, so this obviously makes these codes hard to maintain and tough to reuse, especially for young researchers and programmers that don't have a lot of fluency in Fortran. The other motivation we had is that these codes are all over the internet. So Professor Sigonyenko is kind of the biggest player in this type of modeling. Maintains his own website and has many different iterations of these models. But these models are also used in other planets such as Saturn. Karana has his own version of the model. I created a version for Saturn as well. That's on the Cassini-Mimi page. We have the TS07 model up on the Van Allen probes page, and other people just embed their models. So this is the Hayakorth's Mercury model is just embedded right into the journal article. So the idea is that these codes are strewn all across the internet. Is there a way the purpose of MPy was to kind of create a centralized community location for these type of models in Python. So here's an example of the TS07 model. So this is the model that we wanted to bring into Python first. So we know we can't bring in all these models right away. So the idea was we'll pick and choose the model that we use most frequently and we are most comfortable with. We'll bring that in, but we'll kind of do it in such a way to set up this community library that other people can start adding their own models and we can have just a shared resource. So the TS07 model, as you can see, it differs from the kind of classic Sigonyenko models. So in the classic approach, you pick each of your current systems. So this is an equatorial slice of the magnetosphere. So you can see the symmetric ring current, partial ring current, and tail current. So you take each of them individually and you try to find an analytical expression for that particular current system. The TS07 approach used an entirely different a way to model these currents and instead used just a regular expansion. So this is kind of a boundary value problem solution that you could find out of Jackson electromagnetism, for instance. And as you can see, this general solution doesn't have these kind of artifacts that that more hand-built model does. Everything, it really allows the data to dictate the morphology and not kind of the model developer. The second main advance of the TS07 approach was that it uses a dynamical fitting approach. So every moment in time gets its own custom subset bin of all the magnetometer data. So instead of fitting one giant global climatological type model, it fits every instant in time gets its own custom fit. And then that is repeated for every step. And that gives the TS07 model its kind of dynamical flavor. But it also makes it a very useful model for scientific studies. So we can now fit in a particular substorm event and study a particular substorm event, whereas the TS05 and the earlier type of models weren't as useful for those type of scientific investigations. So the goals of MPy, like I said, the broad goal is to develop this open source community library for empirical magnetic field modeling. But specifically, that's very broad, that we wanted to give users access to this TS07 model. And another specific goal is we want to make MPy a part of the Python and the PyHC list of projects. So some personal goals is I wanted to become a more proficient Python programmer. And I also want to migrate this kind of Java infrastructure that I've built up over to Python. I think it'll make it easier to publish papers and make charts and things like that. So the long-term goals are, of course, to start expanding MPy and bringing in these other commonly used empirical magnetic field models, but also to do this in a community sense, to have different programmers and researchers all kind of sharing code to advance the state of the art of empirical magnetic field modeling. And we also hope to then fully integrate these models with the other frameworks that exist in PyHC, such as that do stuff like field line tracing and visualization and stuff like that. So here's kind of a general just overview of the hierarchy. So the idea is there's a common MPy common. So this contains the building blocks of empirical magnetic field models. So a lot of these models reuse the same fundamental building blocks, the same sorts of description of the magnetopause, the same sort of cylindrical harmonic description. And the idea was that there would be one package that contained these building blocks, and then there would be separate model-specific packages. So TS07D would be our first model-specific package, and then we can expand it by adding future models. Right, so the team is myself. So I've worked with the TS07 and other empirical magnetic field models for about 10 years now. Misha Sitnov is has broad experience in empirical modeling and kinetic plasma theory. He's the original author of TS07D. And then we brought in Eric Winter, who's kind of our Python expert. So he was the one that actually translated all my Java codes into Python and really did the brunt of this project. So here's the progress. So the GitHub project was created. The TS07 Java code was completely ported over, and it works down to single precision accuracy, which is about all we can really expect because the original Fortran code mixed floats and doubles. So it didn't get better than single precision. We fully documented our Python code using Python docstrings and then compiled the documentation using Sphinx. We had to end up Pythonizing a lot of the Java code. Just didn't really make sense trying to bring it over into Python because we really wanted to get to use NumPy and other commonly used Python numerical libraries to make these implementations have the look and feel of Python. And then we ran the code through a variety of linters to inspect and clean the code up. The ongoing problems we have, the big one is licensing. So we at APL need to go through our intellectual property office to kind of give us the go ahead to open source our source code. And so we're working with them to get our license and pretty much just give us permission to make the GitHub project public. And once we can do that, we can then put our documentation on the read the docs page, which requires your GitHub project to be public to do. We ran into this one problem and I wanted to get some feedback from the community. So when I had developed my Java docs, I embedded numerous equations. Basically, I wanted every time I implemented an equation, I put the equation in the documentation, and then that way you could one for one look at the equation and then look at the code and make sure that it's implemented correctly. It doesn't seem like there's a universal way to do that in Python. There is support for embedding LaTeX equations in docstrings, but everything we saw seemed to say that that's highly discouraged because it makes the docstrings not human readable. So I just wanted to kind of know, how did other PyHC projects embed equations into their documentation, or is that just not expected? does anyone have thoughts on that? That would kind of help us out.
Sure. Yeah. If you're asking now, or I can respond for Komodo, the Komodo team. So we use LaTeX all the time in Komodo, both as input to Komodo objects, but also we basically have two places where the doc streams might end up. One is the metadata of whatever function you're documenting. So that's an easy place to throw it, like in a dictionary. But another is, yeah, sometimes they end up in doc strings. It's like, I mean, the thing is, like, it's scientists that are going to be reading this code, so they can easily render that, and so it's not as big a deal as I think people are making it out to be.
Okay, that sounds good. That was kind of my preference, but I just wanted to bounce that off of everyone here. So, all right. The problem. What is that? Oh, I see some hands. Yeah.
For Plasma Pi, we've been trying to use Unicode characters instead of the /alpha or whatever, because those do get rendered correctly, and it does make it a bit more readable to use the Unicode characters directly rather than the LaTeX code when possible.
Okay. It's probably doable for simple equations, I would think. So once you get integrals, and that would probably get harder, I would imagine, but I see some more hands. There's Tom.
Tom Bridgman?
Yes.
Yeah, I'm with the visualization studio at NASA Goddard. It looks like you might have something here that I've been kind of fishing around for some time, and that is a way to make a nice sort of generalized magnetosphere that has good time variation and stuff like that, especially if you can apply it to other planets. So I might be interested in looking at this stuff more closely. I can send you links to showing some of the stuff that I'd done previously. I'd been using a kind of a quick and dirty model that was put together by Lumen and Friesen back in 1979, and I hacked it to put like the IO current ring and stuff like that. But this may be something that I can try to adapt for our stuff to make really polished visualizations for the general public. So I'm really intrigued by this. I had looked at this model years ago. I said, my skills are not up to this, but it's nice to see someone's looking at it. So thank you.
Yeah. Baptiste, do you have a hand up?
No, sorry, I forgot to to put it down. Sorry.
All right, so I just have, I think, one or two more slides. So the other problem we had was performance. When our first shot at the initial port, it was almost 2 orders of magnitude slower than the Java code. So we've been cutting that down by a lot, by basically removing unnecessary function calls. That there were too many layers in the Java code, essentially, and things like in Java, you commonly use getters instead of accessing your fields directly. So cutting out a lot of that has really sped up the code, but it continues to, that's an ongoing thing that we are working on, is to try to make this code faster. So the future, we're continuing to develop this project using our science grant resources, and we've submitted some more proposals to try to advance the project. Like I said, the project is ready to be made public as soon as we get the green light from our IP office. We were trying to have this done before this meeting, but it's been taking a little longer. We're going to continue trying to find ways to speed up the code. We have plans then to add our SST model, which is basically the substorm analog of the TS07 model. And then we also want to look at porting our binning and fitting codes. So right now, we've mostly just been talking about evaluating the model, but the kind of binning and fitting codes are another aspect that would be good to also bring into the MPy framework. And this was just a slide Eric had, just kind of some lesson learns he found of porting Java into Python. I won't go through all of these, but some of these are just things you would expect, like the syntax differences. But there were some major things that he had to work through. I heavily used interfaces to try to make my classes more general. I would hide the class behind an interface. Python doesn't have native interfaces, so he had to do some workarounds to try to still get a lot of the functionality of our interfaces, but without having them. There was implicit imports in Java in the same package. You have to explicitly import everything in Python. Python supports multiple inheritance and Java does not. It's part of why Java programmers use interfaces, because interfaces are kind of a way around the multiple inheritance. And this was a critical thing that took Eric quite a while to resolve, was method names are by name lookup, whereas Java has references by call signature. So you can have in Java, the same method can have the same name if it has a different call signature. And this caused us a lot of problems because I leveraged that a lot in the Java version of this model. So he had to go and clean all that up. So that's pretty much the end of my presentation. So if there's any more questions, or if I might be out of time, so.
Yeah, we're officially running a little behind. So yeah, if you have any questions, feel free to put them in the chat or ping Grant offline. You can put them in the general conference notes so everyone else can see them. Yeah.
Can I make one quick comment?
Sure.
One of the issues about releasing the code is some of the other models don't have licenses. These other ones that we've been trying to reference or use. So that's just a historical problem that's hard to fix. You tell the IP folks, hey, we based it on this. And they say, well, what's that license? And they say, well, it doesn't have one. So that slowed it down a little bit.
Definitely. Awesome. Well, thank you so much, Grant. That was great. I believe the next presentation is the EM toolkit from Joe Plowman.
Yeah, can you all hear me?
Yep.
Great. I will start by sharing my screen. See if it works. So far, so good?
Yeah.
All right. So you should now be seeing my slides.
Yep.
Correct? All right. So let's see here. So I've worked to get some things together for this, but our kind of funding schedule was pushed back about 6 months. So this is kind of just a preliminary demonstration, just some sort of the bare groundwork to have something working to show. I ported one of the simplest algorithms. I built up a sort of a basic structure in terms of some classes and ways of passing the various information around. I tried to base things on IndieCube as much as possible. And I wrote a few simple visualization routines that kind of go on the end of things. So making some of this visualization stuff interactive might be a fun hackathon project, although it looks like your schedule for that is all kind of set in advance. So no worries there. So the next slides, I'm just going to try to step through the basic structure of how this works. To start, way at the top, you have some data source, like for instance, SDO AIA. And then it's up to the kind of the person who wants to integrate that data source with this functionality to write a wrapper for it. And that will be instrument specific, but generally speaking, it doesn't have to be very complicated. All that it needs to do is provide a few different pieces of information to the rest of the routine. A set of data, which is in the form of a set of indie cubes, a set of uncertainties to go along with the indie cubes, and a set of temperature response functions, one for each of the ND cubes. And from that, we put everything in an ND cube sequence, which I call a data sequence. And then there's another set of wrappers that talk to the DEM algorithms. So it takes the ND cube sequence and translates it into whatever the DEM algorithm needs, which again should be super complex sort of thing. This is just to kind of adapt to the fact that there's kind of a wide menagerie of these algorithms, and they have different expectations about what data they want going in and what they return. So the algorithms. So then the wrapper then takes the output of the algorithms back and translates it into a standard set of data for this software to use. And that consists of a set of coefficients that are kind of that specify what the DEM is, a set of basis functions which say, okay, how does this coefficient map to temperature function, and then other metadata like coordinate systems and details about how the DEM algorithm was called, so that the call can be reproduced. And we stick all of that into another ND cube sequence called a model sequence. And then at the end, we combine the model and the data sequence into a collection, an ND cube collection. And from that, we can use that to produce a variety of things. And the intention here, although it's not strictly enforced, is that the data and the model ought to be kind of bundled together, because there are certain things about the model that, like those uncertainties, that you have to refer back to the data to characterize. And so that's kind of basically what the structure looks like. And I'll step through a few of these things in a little more detail in the next slides. But feel free to interrupt me if you have any questions. All right, if not, I will step ahead to the next slide, which shows, for an example of the IA, what these channels and temperature response functions look like. So we're all familiar with what the AIA images look like. There are a variety of channels, and these correspond to a variety of ranges in temperatures. And I've kind of munged the units around here to make them a little bit more comprehensible. Basically, these channels respond to density squared in the sun. So if you have more density squared, you get more data numbers per second. And if you have more density spread out over a bigger chunk of the line of sight, that's the megameters. I'm pointing at the vertical axis on the bottom left here. So that's what the megameters is. And so basically what you're seeing here is that for kind of a typical coronal density and a megameter of depth along the line of sight, you'll get about 500 data numbers per second out of AIA 193. So you can see that 193 is a lot more sensitive than these other channels. You only get 5 out of 335 for the same amount of stuff, and just 3.5 out of 94. And so the name of the game with DEMs is taking the response, taking these images, which are the integral of these temperature response functions against whatever the solar kind of distribution of density and temperature along the line of sight is, and turning it into a function that says, okay, at this temperature, there is the density squared times the depth of material is however much it is. And that's kind of the point of the DEM algorithm. And to do that, it's basically a ill-posed linear inverse problem. And there are a variety of algorithms that do that. And this is the results of one of them. EM Toolkit is kind of intended to kind of provide a standardized way of working with different algorithms and data sources and interacting with them. So this shows the same thing as I showed before, but taking the AAA channels, or there are 6 of them, 3 more in addition to the ones that I showed, and turning them into kind of a discrete set of density and temperatures at, or a set of density squared depth products at each temperature in each pixel. So you can see on the left, it's showing what you get at log t equals 6.2, which is sort of corresponds to the peak of this AIA 193 emission on the left in the previous slide that I'm showing right now. In the center, it's 6.5, which is kind of the peak of the 335 channel. And on the right, it's kind of at the peak of the 94 angstrom channel. As you can see, what it's done is sort of what you'd expect. It's isolated kind of the distinctive features of each of the channels, showing what the kind of the temperature constituents are. And at the bottom, it shows kind of the basis functions that I'm using to represent the temperature, and they're just triangle functions. And the reason for that is that the triangle functions work like a linear interpolation scheme. So you can just take the coefficients that come out and plot them, and most plotting algorithms will just linearly interpolate over the points. So what you get when you just plot the coefficients directly is the same thing as what the basis function gives, which is a kind of a convenient shortcut. One of the things to emphasize that's a little different than the usual paradigm for storing in-dimensional data or dimension data in general is that here kind of the coordinate-like information and structure, which is kind of the temperatures, is carried by the basis functions rather than the temperature, rather than the coefficients themselves. Although generally speaking, you kind of choose the basis functions so that they're localized at a given temperature. So there's some correspondence between the coefficients and the coordinate things, but it's not a direct one. It's mediated by these basis functions. And it's there are a variety of reasons that that's convenient, but it's a bit too detailed a topic for me to try to go into here. So the last thing that I've done is made up kind of a prototype dashboard that you can use to look at these in a little more dynamics. So what I've done here is I've taken the DEM and integrated them against a set of kind of channel responses, which basically clean up the complicated temperature responses of the real instruments, and then overlay them in using the RGB channels on your computer monitor so that you get a color image where the colors represent the temperatures and the intensities and the kind of the spread of temperatures contained in the image. And you can feed this through a kind of a set of things to produce a color bar that basically tell your eye what you're looking at here. The temperature units that I'm using are kind of oddball, but they're more kind of convenient for interpreting these, just because of how the emission and the spectral line responses are structured. But basically, 60 decibel Kelvin units is 1 million Kelvin, and 70 is 10 million Kelvin. So that's really all you need to remember there. And the way it's plotted here, blue material represents hot at around 5 million Kelvin, and red material is cold at around, let's see here, like 300,000 Kelvin. And I've shown a little crosshairs here, which shows the DM at a particular location. I think I mentioned that it'd be nice to make this interactive. So like as you mouse over this middle image, it'll change where the DEM that it's showing, so you can kind of visually explore the space. You can change the amount of crop on this and that kind of thing. So that is basically it. All of this stuff is thrown up in a Jupyter notebook as well. You could probably see here. So you can just call this thing and it'll change what temperatures you use and how to crop it and which point to look at. I've chosen an interesting little point here that appears to have some high temperature emission in some sort of little bright point. And that's basically my talk. Are there any questions?
Awesome. Thanks, Joe. We have time for one quick question. Looks like Rebecca, you have your hand up.
Well, I'm not sure it's quick. Jack, would you prefer to go? Guess not. If you could go back.
I see Jack's question in the chat. I can try to address it here.
Go for it.
So that would be pretty easy. So you would want to have a wrapper with that maps the XRT, that basically provides the output arrays that EM Toolkit expects, which is probably going to be very, very similar to the example wrapper that I've written for AIA. And then you should just be able to feed that in, assuming that the XRT, the XRT images are a map object. It should basically just work. You can feed subfull dist images in if you want. Shouldn't be any problem. I think, and so we're actually planning to add some XRT wrappers as part of the examples for this. So if we make it that far, which we probably will, it should just be included. All right. Let's hear your question, Rebecca.
Well, Julie said when, so I'm just typing mine in the chat.
Okay.
Yeah. Thanks much, Joe.
Yeah, you bet.
Yeah. Go ahead and add any and all questions to the chat. I'll make sure they end up in the general conference notes so other people can see them after the fact. So that concludes our HDEE project kind of updates and wrap-ups for today, and we'll move into a few different project introductions to the community. And I believe the first up will be Sean with a PyHC executable paper.
Yes, that would be me.
Awesome.
Here, getting my screen set up real quick for sharing. That's looking good. Okay. Let's see. Hopefully people are seeing slides.
Yep.
Okay, great. Well, I will, with no further ado, get into it. I'm presenting here just an update on a little project I've been working on with actually a number of you on the call today. This is what I feel like is the first real collaborative like PyHC project. We are, working together with, I think, 2 people that are sort of outside the realm of PyHC, but for the most part, this is a pretty self-contained thing. And yeah, let's see. Let's explain what the project is, and I'll explain why it's interesting. So the domain we're working in here is comparing magnetopause models. We have some real world MMS data that involves some instances of the satellite crossing the magnetopause boundary. And we want to use this data to compare the real world location to where certain models think the magnetopause would be. We sort of worked backwards from the packages we knew we wanted to use toward this problem. We knew we wanted to use PyHC packages to show off what we can do with our software here in this community, but also we need more examples in the PyHC gallery. So we're kind of, killing 2 birds with 1 stone here. Let's see. We're going to produce a couple papers out of this is the idea, and they'll both have the PyHC stamp on it. I think if you Google us on Google Scholar right now, you'll find an abstract where we first announced that we were going to form the group. And then there's this Snakes on a Spacecraft, I think is what the name of the paper is, that talks about issues in our community, and how PyHC could potentially address them, but it's more of a hypothetical kind of thing here. This is going to be, hopefully, we write a real science paper, and then accompanied with it will be a tech paper written by yours truly, kind of explaining the technology we're using here and how we can make our science paper executable. I'll talk about what that means in a second. We are using these packages here at the moment. PySpeedas we're using to get MMS data. SpacePy has an empirical model of the magnetopause, and it can calculate some very helpful things. I'm using PlasmaPy to calculate plasma parameters from the data, PyTplot to plot things, and Komodo has some really interesting interpolation and physics-based model things that I'll get a demo of from Rebecca later on in this talk. Something that's really cool about this, and that I want to actually highlight as an importance of it, is that we're tackling problems that we couldn't solve alone. Neither one of us on this team of people you're seeing here on the screen could do this work alone. But when we get, all of us together, including people we brought on outside of our group for expertise, you get really good work. So let's see. This is making an executable paper, but I haven't defined what an executable paper is. There's actually not a very clear definition, which is surprising given sort of how simple the concept is. The best one I could come up with is an executable paper is an interactive piece of software that combines text, data, and code to enable readers to reproduce every step taken to arrive at a publication's conclusions. So picture a notebook, a Jupyter notebook is honestly not too far off from an executable paper. The only extra thing you're adding here is giving the paper an environment in which to execute so that you have the data along with the code, and you just have one place to go and run everything. So sort of, we've all heard of this reproducibility crisis. I'm screenshotting here the Nature survey. It's lifting the lid on how many people are worried about reproducibility in science. Imagine you're reading a paper and you come across a graph like this in your paper. And instead of just having to trust the image, what if you had the code that produced the plot right above the plot with the data there, such that you could just click a play button and you see the plot get reproduced right before your very eyes? How nice would that be? This is the sort of thing that executable papers can give us here. And we're developing ours at the moment in Deep Note. I want to give a really big shout out to this platform. I've actually been impressed with what we've been doing with it. I will bring up the paper here in just 1 second. I'm putting a link here in the slide in case anybody wants to look at this later. But DeepNote's sort of just, an online website for hosting notebooks. They don't have to be Python notebooks. They can be other languages, but we're doing Python notebooks. The big advantages here are it offers collaborative sort of Google Doc kind of editing. So, imagine one person's writing something in a cell of the notebook. I could watch what they're writing just like you can on Google Docs. Only platform that does this for notebooks at the moment. Interestingly, Google Colab used to support this, but they no longer do. Kind of weird, given that Google Docs is the go-to example for this sort of thing. But anyway, they also give us a nice environment that we can fully customize to make sure it works with our packages. And I think I will switch tabs here to stop hand waving at it and just start showing you all. Maybe if someone could pipe up real quick to tell me that changed properly. I want to make sure that we are looking at DeepNote now and no longer my slides.
You're good.
Yeah. Yep.
Wonderful. Thank you. Thank you. If I could collapse my sidebar over here, I could give us a little bit more real estate, but I'm new to this operating system. There you go. Just upgraded. So we're over in DeepNote here. What interface are we looking at? Here is the notebook. You all have seen a notebook before. Nothing too earth-shattering here. I want to point out that along here in this sidebar is sort of our working environment at the moment. It's actually just like a folder on a Linux box. We have a few different notebooks and a few different folders that have some data in it. And this does persist as I turn the machine on and off. So we don't have to worry about ever having to go back and re-download all of this data. People can go to the URL and things are just kind of ready to go, which is really nice. And we manage all the initialization of the packages and things. I can answer more questions about this platform if people have them at the end. So I don't want to show off our dirty laundry too much. I have these to-do items over here, just sort of things we've been going through. But yeah, I'm going to show how we are pulling in MMS data, how we are plotting it alongside some MagnetoPause data, and we've got some plots and some findings below it. So let's dig into what we have here. These are just some imports. People have seen imports before, don't need to go over that. We are looking at a few very specific time ranges in the MMS data right now. This was sort of curated just to be an easy place to start with because we knew there was interesting MagnetoPause interactions in these time ranges. And later on, we might go through and search more of the data set. So PySpeedS makes it easy to pull in MMS data or any kind of data into the thing really for people who haven't used it. We have sort of just these 3 one-liners here. We're using the MEC data for the location, and we've got some flux gate magnetometer and ion moments data that we'll see a little bit later on. So get the data with PySpeedS. We can feed that data into SpacePy here. I'm making functions out of these because I'll use them to plot here in a second. Just given the location data from MMS, we can pull in the shoe model is what we're using for the empirical MagnetoPause model. The shoe model has actually been mentioned a couple times in the previous presentations we were watching. Just sort of a long time average of the location of the MagnetoPause, pretty mathematically simple. And we're calculating things like, how far away is the spacecraft from Earth and the MagnetoPause, et cetera. Return all these things. Thank you, SpacePy. And then we've got some matplotlib code. don't need to go over what this is, 'cause it's basically just generating plots. I'll just point out that we are looping over the 5 time ranges that we had set up with at the moment. We get the MMS data for the time range, throw the data at SpacePy, and then we plot it. What you get out is a bunch of plots like this. Let's see, hopefully people are seeing my mouse as I'm moving here because I keep circling things on screen. A row is a certain type of plot, and then every column here is a time range. So, you know, in this second row here, we're seeing the orange line is the MMS spacecraft. The blue line is the magnetopause as given by the shoe model. And we're kind of looking for places where the two cross. And actually, if we see in our last time range right here, there is this lovely crossing, right? A little bit after the 40 tick mark there, we can see the spacecraft is inside the magnetopause and then it pops out of it. We can use PyHC plot to plot the MMS data. And we found some interesting things comparing them, especially when we bring in plasma parameters to augment the comparison. But I am gonna pass this off to Rebecca. Actually, I'm gonna let her share her screen in just a moment here to show off some of the Komodo side of this. I mentioned this is a project update. We haven't incorporated Komodo into this notebook yet because it's sort of been in development, but Rebecca is getting close to having exciting things to share for us and add to the notebook. So I think I'll let her show it off instead of hand waving at it. Rebecca, would you be maybe ready to jump in here?
Yep, but you gotta stop sharing your screen.
I gotta stop sharing my screen. There it goes.
Okay, here we go. All right, so I'm going to go through this rather quickly. Oops, wrong one. Show that in a minute. Okay, slideshow, go. Okay, so I'm gonna make this quick because this is one part of a big project. So the authors here are just the Komodo team at CCMC. Darren is hopefully still on the call, and Asher is definitely on the call. Lutz is involved in the European Space Weather Week, so unlikely to be here. And I'm Rebecca. So what we're working on with Komodo is to developing this satellite fly-through, which is present in other packages, but our purpose in developing it at CCMC with Komodo is twofold: to interface to all the physics-based models that we host and to make it fast and easy to access. So I'm not even going to mention everything on this slide, but what I'm going to point out is that we're making this model agnostic. And the point of including it here in this PyHC executable paper is to do exactly that, to include access to a physics-based model to compare to the data and to the shoe empirical model. One thing that's been delaying our process is that the magnetospheric outputs are rather complex in their file formats, and the data is big. Well, the correct term is medium data. So the example of the notebook screenshot here I have is for an ionosphere model, which executed an entire day of data in less than 10 seconds. I'm going to show the example for the OpenS GGCM model, which is the first one we're going to be including in this paper in just a moment. But one of the interesting things here is that you can have three and a half options for your input satellite trajectories. It can either be from an actual satellite, such as MMS, or your favorite one available at the website, SSC Web. You have an interface to that. You can directly input your trajectories through NumPy arrays or whatever data structures, or through a file of a format similar to what I show here, or there's an adjustable sample trajectory function you can use if you don't have a particular one in mind and you just want to see what happens. So I'm going to switch to some results here. So this is an example of the fake flight command. All of these variables have to do with the generating the sample trajectory, and then the rest of them is just naming your output. And for we have this working for the OpenGGCM data. I have 2 hours of data. We're going to be extending this to the entire time range that the model was executed for. For this hour and a half or so, it took 15 seconds to execute about 2 hours of data with a time cadence of 2 seconds. And I wanted to show that first because, of course, no satellite flies this fast at this kind of distance, but this is the kind of output that you get with the interactive visualizations. You can mouse over on it. You have all of the output there. You can zoom. Click the button. You can zoom on different things, zoom in, zoom out. There's other options of visualization I'm not going to go into due to time. Then we have some similar one-dimensional plots. Again, same kind of mouse over. You can have it in any coordinate system. We depend currently on SpacePy for coordinate systems. So nice interface there. You can zoom in, you can do all these kinds of things. But the function that's closest to what we're going to be using in the project is this MyFlight. So basically, or real flight, I'll go with that, which uses a real satellite trajectory. In this case, I pulled in MMS1. So it's not it's close to what we're going to be doing in this executable paper. And notice the time cadence is lower, so we can execute in about 4 seconds for an hour or 2 of data. And this is the plot that you get. Of course, you can zoom in just as before, but mouse over right here. So we're getting close to be able to integrate this into the executable paper, same zoom in kinds of functions. And it's going to be interesting to see how it all goes together. That's my part. Me and Lutz.
Thank you very much, Rebecca. Go back to sharing this notebook here. And we're back in DeepNote, hopefully. So yeah, that's what we'll be using Komodo for. And thank you, Rebecca. And I also have to say Lutz, who I believe is on the call, for all of your great work doing that. That's how we'll be kind of working with some physics-based models here. You know, we've got the shoe model from SpacePy already. We might add a few more models. It sort of depends on where we end up taking this. The actual, science paper hasn't really been all the way planned out yet. We know we're going to be doing, something along here, but whether or not, if we want to make it kind of a replication study or try to do some more things of our own, sort of to be determined. But you can sort of see already how, with actually not that much code, I've really only shown maybe 20, 40 lines of code at most. We can already start to do these comparisons of, how good is the shoe model that we have in here at the moment, this simple empirical model. And I want to show this off here. This is just a 2D plot of the MMS data that we're using here. Take note of the crossing right here in this plot. The two seem to meet right after about the 40 timestamp right there. We're going to take this data right here and throw it into PlasmaPy and see if we can't get any more context on this crossing. I won't go into gory detail on what you have to do to prepare this data for PlasmaPy, but the way we get it out straight from PySpeedas isn't too dissimilar to what PlasmaPy wants. Just use their function to interpolate the times into a common cadence. We needed temperature, so we calculated that really quickly, and then we added AstroPy units. That's basically all we needed to do to, at this point, get these variables, which is everything you would need to calculate pretty much any plasma parameter you would want. You got your B's, your N's, T's, etc. If you wanted to take a look at this notebook, we have examples of calculating anything you could want. You got your plasma beta, alpha speed, ion gyro radius. They're all just one-liners. PlasmaPy makes this very easy, especially once you have those variables just sitting around. And I'm going to plot them all. If I can get this looking pretty again. So here's a time series of every plasma parameter that we were calculating here. And something that I noticed just glancing at the notebook is there seems to be something happening right along this vertical line here, sort of just after the 30 tick in between 30 and 40. That's also in agreement with what we're seeing over here in this plot, where this sort of seems to be where the data changes right between 30 and 40. Now that disagrees actually with this right here, showing that the spacecraft crossed the magnetopause as guessed by the Shu model, right after 40. So that leads me to believe that actually the Shu model is a little bit off in this case, and it would have been a little bit closer to Earth at this time, meaning the spacecraft would have crossed just a little bit earlier. Now, not going to stake my claim into that or anything, I could be more scientifically rigorous there, but we're already able to sort of start to test the validity of this one model. And the idea for this project is to start bringing in more models like we can with Rebecca's code. Then we'll be publishing some kind of paper on it. And that's where we get back to executable papers, because now you can sort of imagine if this wasn't just a simple notebook showing off, how to use these packages in this sort of workflow, but instead, if we actually just put the whole paper here, we could have the title, the intro section, you have headers, all sorts of normal things you would have for a paper. But here, where we're sticking out of the plot, we're going to leave this code right here for people, and they have the MMS data right next to it, and they can, go off and work with it. This helps people reproduce our work. This gives scientists a better launching point if they would like to extend our work. And it lets us, share the work better. The only, obvious caveat here, which people might be, saying to themselves at this point, is that journals do not accept this as a form of publication. So, really the idea is going to be to publish a normal paper, but then have this executable version of it. And, say we can link to it, say at the end of the paper in a footnote or something, say for an executable version of this paper, see here, and we'll have like a DOI. Not sure if DeepNote is actually the platform we would want to be leaving this in. There's plenty of other options. Binder is a good one. We're actually using Binder in the PyHC gallery at the moment to run examples, but people have used that to share executable versions of their publications before. There's also another tool that will scrape a GitHub repo and generate one of these kinds of things for you. I think DeepNote actually might do that too, but I haven't hooked it up to do that yet. Point is, we will sort of decide what the mechanism for that is going to be, but we can share the science paper, and then the tech paper that I'm writing will sort of describe all the nitty gritty details of how to do this with this tech stack. And that's where we're at with this project. I could say more, but I think I will kind of wrap up now and open the floor for questions. I've seen a few comments coming in the chat, but I haven't been checking it closely for questions for real.
Yeah, it looks like Ryan asked a question. I think we could cover that one. And then if people want to put more questions in the chat and we'll move on to Alex's presentation after, that'd be great.
Let's see, what was the question here? Is there a way for readers to add comments? Oh, yes. DeepNote does have its own comment section here. I can just click this little button right here to add a comment, and that will be public. They also, DeepNote does support making one master copy of a notebook and then letting you sort of fork and branch off things automatically when you open a link, so that, someone could fire up a session of this and fiddle with it as much as they wanted, leave whatever comments that they felt like, and it wouldn't change the original. Or you can let people just change the original. That is all fine too. Jupyter Hub, Binder, these other places, I know are starting to add comment support. Binder hasn't quite gone there yet, and it's been on Jupyter Hub's roadmap forever, but also not quite there yet. So it is a factor of here, but it sort of depends on what platform you end up publishing with. You're welcome, Ryan.
Awesome. Thanks so much, Sean. We're running a little behind, so we'll have to keep going, but please feel free to put more questions in the chat or ping Sean offline. Yeah.
No worries.
Yeah, thanks so much. Alec, you're up next with PyHC and Jupyter Hub, which is nicely related to what Sean was just talking about.
Hey, all right. Thanks, guys. So I'm Alec Engel. I work at NextGen Federal Systems. We're an enterprise IT company. I'm a data scientist really with a background in heliophysics. So to get started here, let me go full screen and feel free to interrupt here along the way. I can't see the chat or anything. So just, we can keep this informal, but I am going to move pretty quickly, but don't let that get in the way of interrupting me. So please. All right. So what is PanHelio? It's an ecosystem for streamlining heliophysics science and space weather, O to R. And so here are the key takeaways. It's an ecosystem for collaborative and repeatable heliophysics data processes, science, and forecasting. Why do we want this? Other than the obvious, bring state-of-the-art data access and analysis to state-of-the-art heliophysics to streamline science. How do we do this? Pretty typical technology suite. So APIs, databases, widgets, a collaborative ecosystem like Jupyter Hub, external catalogs and files. So whether you legacy code, legacy files, or CSV files, catalogs of events and things like that. If you work in a Jupyter Hub and you got Python, you can do data fusion. You can do machine learning. And then of course, really pertinent to this community here is that we can stand up an environment that has all these wonderful heliophysics community libraries working together and really start to understand what everybody is bringing to the table and really identify roadmaps on, hey, I should work on this, you know, I'm going to drop this capability because this library fills that need more effectively. And so just really alignment of this community. I just mentioned briefly, you know, data lakes are great, but if they get too big of a lake, it's hard to do. And same with software. If we get software lakes, we just want to control that. So all these libraries can be in something like the PanHelio ecosystem, and of course it's cloud hosted. So here's the architecture. So our project, one of our main focuses of PanHelio in terms of an application has been space weather prediction using machine learning. But this is your typical data incoming on the left. So you might have operational data from NOAA SWPC, you might have model data coming from the CCMC, Space Weather Trek, you might have metadata coming from the HEC or the SHARPS. And then again, this community has great APIs from some existing libraries like SunPy or PySat, where you're able to reach out into those data repositories and bring that in. You can cache that data, or using some very clever capabilities developed by, again, the open source software community, you can bring that into your Jupyter Hub instance, and you can start playing around with the data. In terms of having a database is very attractive, especially for in situ data, not terribly big compared to some of the solar imagery data sets we get. And then you can also host mission data, potentially, such as upcoming SMEX missions, and really start to align them already being in the cloud. And again, the libraries are on the top there, just some examples. It's not complete by any means, but you've heard from some of them already, such as Komodo, PySat, SunPy, Chianti, MagPy, PlasmaPy. And then on the right, you have your more generalized libraries, which you really want to align to as much as possible, because those are the ones that are under constant scrutiny by open source developers and are really solid for using data science and analysis processes such as X-ray and DASC and bokeh. And then directly from within the hub, and we do this all the time during our pull requests and our sprint reviews here at NextGen, we just do it directly from the Jupyter Hub, which is very convenient. And then Ryan, I like your comment on making a discussion, and perhaps there's some ways of linking that directly from a Jupyter Hub instance into the GitHub repo so you can track some of those comments. And then, of course, operators, forecast scientists, STEM, REU programs can all take advantage of such an ecosystem. All right, so parallels Pangeo to Panhelio. If you haven't heard of Pangeo, go check out Pangeo. The link is there. So the Panhelio goals are very similar. Foster collaboration around open source scientific Python ecosystem for solar, interplanetary, magnetospheric, ionospheric science. So this really aligns well with the Python heliophysics community. Support those helioscience packages, and then improve scalability of those tools to go out and do petabyte fun. So what's currently being done in Panhelio? So we were able to quickly take that notebook that Sean just demonstrated and get it up and running in the Jupyter Hub in about a day's time. We created a separate kernel called the PyHC kernel within the Panhelio Hub. Plasma Pi, Sun Pi, Komodo Pi, Spedas, Space Pi, Spedas, sorry, I always get that wrong. And then PyT-plots also in there as well. Would love to have a debrief on lessons learned. Harold, the software engineer who leads the development of Panhelio, did have some struggles. One thing was kind of weird. Sun Pi went from version 3 to 2.0 for some reason when we imported some of these libraries, and we didn't take the time to trace where it did, but we got it working for the most part, except for I think one plot output wasn't working. But would love again to have a debrief with some of these authors here and Sean's team there regarding what we found. This was the main application that we're currently wrapping up here, and you can see the collaborators there on the right, the institutions. One of the struggles that I've seen in this field is the associated catalogs of events, which is really something you want to have. So this flare is associated to that SEP, is associated to that shock, that CME, radio burst, geomagnetic storm, what have you. And so we developed this sort of dashboard here that takes advantage of the underlying database, which is GOES, X-rays, protons, electrons from 1985 through present, and then your ACE and Discover Solar Wind from 1997 through present. And it gives you an interactive display in bokeh, and along with the data tables on the right, if you have the right permissions in this environment, you can actually edit this catalog and make it collaborative. So hopefully we'll agree 90–95% of the time that this flare starts here, start end time is associated to this SEP, this shock, this CME sheath, and so on. So that's the idea. So we're really trying to hammer this out. And then all you have to do through the API is like, hey, give me the associated catalog that you have for radio burst, shock, flare, SEP, and it'll give it to you. And then you can also take advantage of those start and end times and then throw that into another API, whether it's PySat or SunPy, and then take advantage of that API to go out and get another data set that you previously didn't have. So from my perspective, the foundation of having these associated catalogs and events is really great. And it's very similar to Sharps as well with their bounding boxes and being able to say, hey, I want to go study active regions that produced X-class flares. And so how do you sort of make that available for folks in a streamlined fashion? So a mini project here, AIA radial filter. This is actually a project I was involved in back in the day at the CFA with Steve Cranmer. He now has a graduate student, Chris Gilly, who's working on this. That might have some advantages for Punch, but Gilly was able to get whitelisted on the Panhelio ecosystem and put all his GitHub code repo up on there and execute it. And so excited to work with him and some other aspects that we're working that can really build on top of his work there to see some coronal dynamics. We have a good intern program here at NextGen. So here's some of the college intern projects that we have going on. Like I said, we have the Proton API for GOES 1985 through present. So one of the projects on the left there is, hey, top 50 geomagnetic storms. What events have ESPs, energetic storm particles? And then let's see if we can predict the time of arrival of the shock based on time derivatives, perhaps doing some time series machine learning of the arrival of those CMEs. And then on the right there, another intern project to visualize CMEs as they pass by Earth. Predicting BZ is good. I also think along with that, we should be trying to predict counterclockwise, clockwise type of stuff. So we're amassing a database of these sort of events and doing some metadata calculations in terms of rotation as they pass by Earth and hopefully doing the appropriate translations. So just a couple of mini projects there. So what's being planned for Panhelio? So we are endeavoring to work with Anaconda on some of this really cool stuff that is coming around the corner that I think the heliophysics community, especially the heliophysics community that's concerned with large amounts of data and how and what to put on the cloud potentially. So we have a couple of proposals in to make X-ray work with the World Coordinate System, to take advantage of a new and upcoming library called Kerchunk. It's a great name, to work with FITS files. So I was talking with Jim Bednar from Anaconda and Martin, and they actually have a wonderful notebook that they were able to hand off to me last week. So similar to Sean, we got it up and running in about half an hour. And on the right there is a notebook of about 30 gigabytes of SDO data being accessed from our cloud instance. And that 400 gigabytes of SDO data is in another cloud instance, only in FITS files. And so we were able to get that and visualize the 400 gigabytes relatively quickly. It's still not as quickly as if the AIA data was in X-Array on your local cloud instance, but it certainly streams it up pretty quickly. So hopefully you get happy users when you can implement these types of technologies. This is a project I really want to revisit. Joe, you might be interested in this, but this is an IDL plot if you couldn't tell. It's ugly. I'm sure you can make them better. This is about 11 years old, but I wanted to do some annotations in bokeh, basically revamp this so it's in Python, and you do little bounding box above post flare loops, and then you can look at the cooling of those flares. If you're able to streamline this, you can probably do hundreds of flares in a week, and then do the analysis of the cooling of the plasma loops, and maybe get some interesting things, compare them to Eve, or do some other sciencey stuff that I probably wouldn't be too good at. You know, we always need another CME annotation tool. So let's again put it in bokeh, holo views type of tools. Let's generalize this stuff so it's in Python. And so this is just an example of another project that I want to do, and perhaps, you know, again, these projects are tractable for college interns to do, and really building up our tool set for what we have. All right, so last slide here. No pretty picture. Panhelio community, 17 users, 7 organizations. We would love for Python heliophysics community folks to join. If you join, I'll make sure you get 50 gigabytes of storage for your project, or per user, depending. We'll get the package built, the kernel that you need, whether it's this library, that library, combination of libraries. It could be used for future hackathons for this community. And there's my contact. That's all I got. Thanks, Julie.
Thanks, Alec. Does anyone have a quick question for Alec before we move on to our last presentation?
Really quickly, could you remind me how you handle dependency management in that environment?
Yeah, unfortunately, Harold is not on. He was on briefly. I don't see him now, but he was focused on that. So we just spun up another kernel to do the build. We basically took what we had in our already existing state, and then we duplicated it and said, this is the one we're going to test and muck around with. And then I think the order of operations was like, okay, Plasma Pi, Pi Speedas, and things like that. And we just see what worked and what didn't. And I know, Sean, you were supporting Harold a little bit for some of the questions he had regarding that. But unfortunately, I was not paying attention too much. I was working other stuff. And
That's
that's
okay,
why
but
that's why I want to debrief with you guys.
yeah, is it still mostly you get one compute environment for yourself where you pick a version of a dependency and you live with it?
I think it just depends, right? I mean, ideally we really want one environment for folks to work off of, and then if somebody comes in and says, hey, my library is not there, it's like, okay, let's duplicate what we know, what works, and what we have so far, build it, and then if it works, let's make that the main one now, provided that there are no errors. But of course you're going to end up having multiple sort of dev environments inevitably, because things are always in flux.
Cool, thank you for the answer.
Yep, hope it was sufficient.
Awesome. Thanks, Alec. Well,
Yep.
if anyone else has any extra questions for Alec, put them in the chat, put them in the general conference notes. We'll make sure they get answered. So the last presentation of today we have is from a new member to the community. Let me know if I said your name wrong. Ijit Itek, with
yeah,
the
it's
solar
very.
flares. Oh, cool. Awesome.
Oh, so it's very close. I was about to say sorry.
Okay, I got close. But yeah, he'll be presenting on a solar flare detection algorithm. So go ahead and take it away.
Yeah, let's do that. So I'm going to share my screen and check a couple things in here. So if I can figure this out. Perfect. So I just realized I have to give permission to Zoom for letting me share my screen. If you allow me 1 second, I will just click that and
sure.
I might need to quit very quick and come back. Let's see how is it.
No problem. And yeah, we'll probably run over a little bit with this presentation. So if anyone needs to leave, no problem at all. We'll continue recording till the end. Also, after Yijit is done with his presentation, I was thinking of leaving this open if anyone wanted to stay on longer and ask some questions or chat. So.
All right, so I'm trying one more time. Okay, so can everybody see my screen at the moment?
Yeah.
Perfect. Okay, yeah, sorry for the little interruption out there. Hi all, my name is Yiğit Aytaç. I'm a data scientist at AWS. And so basically today I will share with you, to be honest, I just learned today, what I'm going to share is basically an executable paper. And thanks to Sean on that. So this work basically, if I put this in a frame, the main motivation behind this work basically to be able to create a proof of concept to demonstrate real-time object detection for solar events from the full disk images. And the work was basically built to support our one of our customers at NASA, Janet Kozra. She's a program scientist at the Heliophysics division at NASA headquarters. So basically what I'm going to do today is click through some basically cell blocks, so just to be able to show you what is the main approach we took and followed through to be able to create an object detection algorithm to be able to identify these solar flares. So basically that's it. I'm going to share with you two main notebooks, Jupyter notebooks. And in the first part, I will walk through basically how we managed to find out or prepare the machine learning data set in the first place. And in the second notebook, I will show you the basic steps to be able to train an object detection algorithm with the single shot detectors, with the ResNet backbone and things like that. And I will basically just show the results at the end, and there's going to be maybe a couple of extra information about how to do this type of operation in, you know, CPU versus GPU type of environments, and if you end up using AWS, and what will that cost you, and what will be the, you know, different approaches and different options along the way. So that said, let me start with very fundamental first couple steps in here. So again, you know, we want to end up having an object detection algorithm that can detect flares. So this can sound like a very broad, you know, like what type of flares, and, you know, when the flares are observed first, and what will be the threshold for the, you know, the intensity of the flares. So I do acknowledge there might be so many different questions, and I want you to just keep in mind, I had a PhD physics PhD, but not exactly in heliophysics. So many things in this session so far is quite new to me. So my approach to this is more fundamental, that in a computer science standpoint, can we just, you know, identify a specific shape on a full disk in solar disk to be able to tell if it's a coronal mass ejection or it's a flare, and so on. So that said, I will rely on, basically we relied on heavily on the SumPy library. And within SumPy library, we use two specific modules. In first, we use the heliophysics event knowledge base, HEC, repository to be able to just find the specific events that we want to study. And I will get there in a second, but in this case, we are focusing on the flares. And in the second stage, we need to actually have a actual image in a raster data set to be able to, you know, search, and actually to be able to train the model first, and then search in a similar environment for similar type of events we trained for. So what I'm trying to say here is basically we have HEC and FIDO modules within the SumPy to be able to, you know, find and acquire the data in the first place. So again, you know, this is executable as it goes. So I will just click through a couple of things in here just to share with you all in situ. So there are a couple of libraries that we want to make sure we have in our system. And, you know, these are probably not too unfamiliar to you. So this tree comes with the SumPy and the extra extensions that within the SumPy we will run that will be needed. So all these things are satisfied. So I'm going to continue clicking through these parts while I speak about, you know, what will be the need for those. Again, you know, I will probably, this is going to be available, this notebooks too, so you can just, you know, dig in what are these libraries doing specifically. But I just want to jump in here, pull in the data portion, and how we shaped our approach in the first POC that I'm sharing. So basically, we put a threshold for the flux rate for the flares around 3,500. And this 3,500 per centimeter square second for the flare events was our lower limit. So we want to collect everything above this flux threshold and specific type of event, which is the solar flares. So when you run this, it's basically pretty quick to search through the heliophysics event knowledge base within this dates, which we basically picked from 2010 and 2018 time windows. And basically in here, within given the dates and the specific type of events, we were able to acquire 264 events in this case. So I will mention in future that there's actually a larger data set that we reduced the flux rate to 2,500 that let us actually pretty much, you know, acquire more data to be able to train the model and be a little bit more sensitive to similar type of flares in a very core of the study. So when we look at the heliophysics event knowledge base, this is very similar to Pandas data frame. At the same time, it's not exactly Pandas data frame. So in the next stage, we will convert it to data frame, but I just want you to show you a couple of things that we are mainly interested in. So there are, you know, quite a bit metadata involved in each font in here. So, you can find out the event coordinates for that specific event, and you can, find out the units or the peak time, or you can get into like more of event start and end time times type of information. That said, our main focus is in here building an object detection algorithm. So we want to know where on this image the event is happening, and basically, we just need a bounding box for that event. And in addition to that, we might need to keep extra metadata in this stage, such as the wavelength and the instrument information when the image is acquired. And so basically we can just make use of this extra information, since considering different instrument might have a different dynamic range, and it might be a different resolution, and so on. So at this point, once we acquire this the HEC table, so I'm going to run the next cell to be able to convert everything that we got there to basically pandas data frame. It's a little bit easy to look at. Again, we have the bounding boxes located in here, and we have the different style of annotations provided, so we can pick and choose. We created both for YOLA format, and we created for also a single shot detector and the COCO dataset format. So in here, the basic information is acquired in this data frame. So this is basically the step we are taking in here. So let's look at some of these, and maybe I can show you our method of pulling the data using the FIDO search option. So basically, this stage is pretty straightforward. That what we are ended up doing in here is just looking at the peak time of this specific event, and we are pulling the data within 10 seconds the time frame of this peak. So last time I run this thing, actually, I can do in-situ updates in here to just make sure that we are pulling something that we can look at. In here, what we are looking at, basically, FIDO search is being done, and it finds basically 2 images with specific wavelengths of the detector and specific time window. And again, we are specifying the instruments as well. And in this time window, we have 2 full disk images. And if we just go ahead and download them very quick for this test, I just want to show you the what we are acquiring at the end. All right. So once we extract and plot the images for those, oh, this is rising. So let me go back and just make sure that we have something already run. So this is basically the step. So this is my back like just the same notebook, but without the error. This is what we will get at the end of it. So if we just look at the specific image after we downloaded it, so basically this is what we would end up having as a metadata format of the image. So you can look at the the coordinate system in ArcSight, or you can just look at the pixel values, which later we basically associate this pixel values with the coordinates of the event, right? So this is pretty much what we need from this little survey and data acquisition part in our site. So next couple of things in here I will run through is basically just converting bounding boxes to specific annotation formats that we have. So if you just look into a couple of examples, again, I'm having the same error. That's very strange. Sorry about that. I just ran this thing this morning, and it was running without any issues. So I will just restart my browser and restart my kernel. I think I can also. Yeah, there we go. All right, so I will just rerun this cell very quick, and then I will show you if it's going to work or not. I'm sorry, folks. It looks like one of these are giving me the problem in here. I will just update this very quick and then move on with the training part. So I think the main takeaway in here, when it's running in the background, I can just close this loop. The goal in here is just basically, having the data sets pretty much ML ready. That said, we just need the bounding box coordinates for a given image to be able to feed into our training algorithm. So if this runs within next half a minute, I will just make it sure that I can show a couple of examples of the bounding boxes, and then we will move on to the training portion of the notebooks. And I apologize for the inconvenience and wait time in here. It's really unexpected. Okay, so there's no need to wait too long. So this is basically the representative of that image with what I was planning to show you. So this, the full disk image acquired with FIDO, and we got the bounding boxes information from the HEC, the heliophysics event knowledge base, to be able to gather these two pieces together to feed into training algorithm. So let me move on with the training portion of this, and then I can basically run this up with the conclusion at the end. So what we are doing here is the second part is we are going to use a GPU-based instance for training and CPU-based instance at AWS to be able to train, to be able to prepare this data set. So in this case, I already run this part, so I'm trying to minimize the errors in here. So again, we have a set of libraries provided in here, and to be able to train the models within the Amazon Web Services, basically, we just need to define a couple of roles within the SageMaker to be able to access the data and update the data and to be able to initiate the trainings. So main couple steps in here that from the previous set that we need to know is how to convert data set to specific format, right? As I mentioned earlier, some annotation formats can require you to keep the center location and the height and width of the bounding box. In some cases, we need an xmin, ymin, xmax, ymax. Another way of saying it's basically the bottom left and the top right corners of the annotation box. So in this case, what we ended up doing is basically training a single shot detector. And this algorithm requires us to be able to format our data set to this xmin, ymin, xmax, ymax format. So basically, we created the data set with annotations within this format. So this couple next step is basically showing us the process of this approach. But the main takeaway in here is to be able to split the data without creating any bias between the training and validation data set. So in this training portion, that our main focus is using the data set from specific dates, which is exactly, to be exact, it's 2010 to 2014, to be able to create this training data set. And from 2014 to 2018, we used this data to create the validation data set. And in here, you can see the total number of images after we put the flux rate to 2,500 ergs per centimeter square per second. We have a total 3,505. So basically, in here, we have like a 80 to 20 split in validation and training data sets. So I'm a little bit afraid of clicking any of these cells now because I don't want to interrupt the flow, but I have the results to show. In here, this model that we trained has the MXNet framework. And basically in MXNet framework, if you're training your model, that the process is basically creating this record IO format to be able to feed the data into training structure. So this is basically the cell that we create this format, and we push this data to S3 buckets to be able to put later in the training loop. One of the useful things, and I guess this will be one of the effective approach in here that we are having is, so this notebook's cell is running on a CPU instance, and it's basically not a very strong machine. And we can control to spin up and down a GPU instance within the CPU in here is shown. So basically, I already mentioned the converting the record format and uploading record to S3 buckets. So this will be something that could be, you can follow through once you have the notebooks. And so basically the training portion at the end that I just want to cover in here without run out of time is basically the essence in here, as I mentioned earlier. So we have the data that we want to train for a specific event type, and then we have the Docker image provided within the SageMaker for this type of training. And again, this Docker image is basically MXNet framework using SSD model within. So it can be used for both training and a deployment portion of the model as well. And in here, so basically there's a couple steps in here that we are, I'm showing is training image obtained first. And basically this is the location of the image and this is the name. And we have to define the location of the data, which previously we uploaded this data to the specific location. And we also have we have to establish what type of instance we are going to use during the training. This is MLP3 2x large instance, contains basically one GPU within. So we are going to use this one. And you can define a couple of other metrics like where to put the artifacts at the end of the training, which are pre-trained in this notebook that you can update as you wish. But this is the basically location and the name of the job. So once we define this very specific things about the SageMaker environment and the location of the data and output of the data, now we can actually define the hyperparameters specific to the model that we choose. So again, most of these parameters can be updated and modified for different type of applications. So for example, if you have something different type of event instead of solar flares. And let's say you want to know where the location of the sun grazing comets or coronal mass ejections and things like that, then you may need to consider some update on these parameters to be able to optimize the model based on the data set, based on the given data set. And so finally, I guess once we establish this portion, we can basically continue to just upload the data for training and validation, and we can submit the training job in here. So I think, so again, my notebook instance for some reason is out of sync. I am not going to run any of these for now, but I will show you the results in here since the model is already completed running. So so this is the logs, but I just want to jump back in SageMaker environment to show you the specific of the training job results. So in here, if you look at the training jobs, that this one is completed basically yesterday, and it took total 44 minutes. And just extra information in here for specific type of instance. In this case, we are using. This is a P3 2x large with a single GPU. And you can find the details if you want to run this algorithm within the AWS, or, this will be basically reference sheet for the pricing. So for this particular model, we use this instance, which is $3 roughly, and the model training took about 44 minutes. So basically, you can train the same model for different type of object or the same flare events, about $2 end to end. That will be the total cost. So if you go back to the model results, you can visualize all the training jobs in here. So again, if you just go to this one that we trained previously yesterday, so you can basically scroll down. You can find all the information about the model and the information about the specific hyperparameters. And finally, you can visualize the basically compute utilization overall for your GPU and memory and disk. But the main takeaway we want to have is basically validation MAP score. So in this case, since this is an object detection algorithm, mean average precision is used as a one of the popular metrics. Maybe F1 will be the other one, but in this case we use the mean average precision. And so basically, if you look at this chart in here, that we are looking at the 0.6 range just after 30 epochs. That said, maybe we could extend this training a little bit longer, since there's still a positive trend in here over time. But at the same time, 60, or this is basically 0.62 MAP is still pretty good for this type of object detection algorithms. And you can also visualize the training process and cross entropy and smooth L1 scores for your loss functions. So to be able to just assess the model is training well and things like that. This is just another platform to visualize these results. So if you go back to the main notebook, and I will just show you a couple of results, and basically I will conclude my talk in here. I guess once the model trained, we can make sure that we are visualizing everything and we are understanding the metrics in this notebook. And before we show or before we run results, we should be able to deploy our models. In this case, you can choose the type of instance that you would like to deploy. And this case, we are using a compute optimized instance type to be able to deploy our model and to be able to run a real-time inference on this model. So that said, this is the test model portion, and we have this function in here to be able to visualize detection for a given image file. We can create detections, and in this case, we have only single classes, but with the specific threshold, we can show results. So here are some of the results that I'm going to go ahead and show, since everybody has the notebook available to study the details. So these are the images, and the threshold in here 0.6. It's pretty high threshold. So most of the case we are not seeing any flares, but let me see if I can find one in here. So for example, this in here, there's flare in here corner. This is a true positive with this confidence score attached to it. And we have probably missed one in here, and a couple of others. So I think in this part, I can show you one full, like an end-to-end event. It will be a little bit easier to grasp what I'm talking about. So this is the same model run against a set of images, but these images are obtained from within the validation dates, and basically these are not used in training. And yeah, so if you just watch this process, so here is our true positives. Pretty much the flare is going on, and the model is looking at this in a video stream, and so basically we are able to make predictions 10 frames per second fashion. It's pretty quick, and the goal again in here is just be able to live stream this data to make predictions. And in a broader perspective, we want to make predictions not only for flares, but any type of event can be happening on the surface of the sun. So with that, I think I'm going to go ahead and end in here. If you have any questions and follow-ups, I think I can try to answer. And yeah, this is pretty much what I got. Yeah, thanks for listening.
Thanks so much. Does anyone have any questions? If not, or if you're thinking of a question and want to ask it later, I'll make sure in the general conference notes to include all the presenters' emails so you can go ahead and ping them offline.
Yep.
Awesome.
Thank you.
Yes, thank you. Thanks everyone for showing up today. For those who were able to stay a little late, I'll go ahead and end the meeting. If a couple people want to stay on and keep asking some questions from each other, feel free. But yeah, that's it for day one. Thanks, guys.
Thanks, Julie.
Thanks, Julie. Bye-bye.
Thanks.
Thanks.
Bye, everyone.
Bye-bye.
Thanks.